In the early 19th century, electricity existed as a violent, chaotic force of nature. Early engineers weren't trying to optimize it, they were simply trying to survive the act of taming it. By 1858, humanity attempted its most ambitious feat yet, harnessing this power across the floor of the Atlantic Ocean to link two continents by telegraph. To survive the crushing pressures of the deep sea, the cables were massive. Engineers shielded the core with heavy layers of gutta percha, hemp, and thick iron wire, creating a physical bridge thousands of miles long. The connection worked for only 3 weeks. The project failed because the lead engineer relied on a flawed theory of how the cable operated, pumping excessively high voltages into the line until the insulation literally fried. In these early decades, electrical engineering remained a blunt, macro-scale frontier. The rules of physics were being written through burnt copper and incredibly expensive failures. By the 1880s, the struggle had moved from the oceans to the cities. But as engineers began wiring urban grids, the same lack of mastery brought deadly consequences directly into the streets. Early power companies created a tangled web of uninsulated, high-voltage alternating current wires above the sidewalks. During the Great Blizzard of 1888, these live lines snapped and fell into the snow, resulting in several tragic electrocutions. Thomas Edison, who held the patents for the competing direct current system, weaponized the panic following those deaths. He launched a campaign to convince the public that alternating current, or AC, was too lethal for domestic use. To prove it, his team held public demonstrations where they electrocuted animals using his rival's technology. The rivalry reached a grim peak when Edison colluded with the state to ensure the first electric chair was powered by a Westinghouse AC generator. He wanted the world to permanently associate his rival's current with the state-sponsored taking of life. This era proved that before the grid could modernize, engineers had to overcome more than just technical hurdles. They had to survive our own ignorance of the physical rules of electricity. Alternating current won the grid because transformers allowed us to step voltages up for long-distance travel. But despite using it every day, the formal rules of the circuit are still widely misunderstood. Take the common myth that current takes the path of least resistance. In reality, current splits and takes all available paths, flowing in amounts inversely proportional to the resistance of each one. There is also the persistent belief that current is the only thing that kills. While current does the damage, the voltage of the system is what determines how much energy is delivered during a fault. While these debates continue on job sites, theoretical physicists realized that our map of electrical science was actually missing a massive piece. For over a century, the foundational laws of electronics identified only 3 passive circuit elements: the resistor, the capacitor, and the inductor. In 1971, Leon Chuan noticed a mathematical hole in that symmetry. He proposed the existence of a 4th element that bridged the gap between current and charge, the memristor. This element would be able to remember the amount of current that had flowed through it, even after the power was disconnected, by coupling electronic and atomic transport. For nearly 40 years, the memristor remained a mathematical ghost, a perfect equation that no one could physically prove existed. That changed in 2008, when HP Labs researchers finally realized the theory in the physical world. They didn't build it with massive cables or heavy iron. They achieved it by manipulating titanium oxide at the atomic level, moving ions across a distance of just a few nanometers. This chart shows how micro-scale mastery is transforming industrial hardware. By engineering gallium nitride power electronics at the nanoscale, we create components significantly smaller than legacy silicon. In electric vehicles, this drastically shrinks the propulsion system's footprint while increasing efficiency. These atomic-scale components offer 8 times the power density of previous hardware. As they replace legacy silicon, the bulky transformers and massive cooling systems that once defined our industrial landscape begin to shrink and recede from view. We are now pushing that miniaturization to its limit with smart dust, computers the size of a grain of sand that require no external wires or batteries. This led to neural dust, microscopic sensors injected to monitor nerve activity. An external patch sends ultrasonic waves through the skin, vibrating the sensor's tiny crystal. This generates power to bounce a signal back, transmitting nerve data without wires. The journey from the first ironclad Atlantic cable to a microscopic neural sensor represents a total victory over the chaos of raw current. We have moved from a blunt struggle against nature to a world where the circuit is no longer a dangerous hazard overhead, but a silent, wireless part of our own biology.